I know you. And I know why you're here too. You want to find out about this quarter game. That's great. Let's draw it up here with a marker. So here's a bin, and into this bin goes 6 quarters. Okay, and they all drop down in here, and this is like a plexiglass bin, so you can see what they are, right? So if 4, 5, or 6, you want the conjunction, don't you? Me too. 4, 5, or 6 heads, and we are going to win. And what we're going to win is a jackpot. So what I'm going to do is I'm going to use the letter J to stand for a jackpot. Here we go. Win J. All right. Now, what we want to do is find what this jackpot is that makes this game fair. So, find the J that makes this fair. What fair means is that the expected value is going to equal the probability of winning times that jackpot. So that's going to be this. This translates to the expected value equals the probability of a win times J. So what we have to do is find the probability of a win. We know the expected value because we want this game to be fair. This fair expected value is that's just a definition. That's that, okay? So that's going to be equal to the price to play the game. And the price to play the game happens to be $1.50. So if on average people are winning $1.50 when they play this game, that's on average. So some are winning, some are losing. And of course, when you win, you're going to have to win a bunch because the odds of winning this game are not 100%. So we're going to find out what that bunch actually is. And we're going to find that out by using Pascal's triangle. So here we go, Pascal's triangle. Starting with 2 1s. A 1 and a 2 and a 1. And if you can add, you can build Pascal's triangle forever and ever. Because of course, every number is the sum of the 2 numbers above it. So this 3 we get from adding 1 and 2. This 6 we get from adding 3 and 3. Because we started with 2 1s here and we're working out this way, this triangle is symmetrical. So as you're working on it, all you have to do is get to the middle and then just work your way down. You don't have to keep doing the arithmetic over and over again. Only a couple more rows to go, and there's a reason why. You can ponder it whilst we draw. 1, 5, 10, 10, 5, 1, and 1, 6, 15, 20, 15, 6, 1. Why do we have to go no further? We have to go no further because there are only 6 coins. Following the natural number diagonal down, we know this is the row that we need. So if we look at this triangle here, the 1 and the 1 would have been if we were tossing 1 coin, counting the number of possible heads. We could have had 0 or 1. Tossing 2 coins, we could have had 0, 1, or 2 heads. Tossing 3 coins, we could have had 0, 1, 2, or 3 coins, etc. Down here, we're tossing 6 coins, so we could have 0, 1, or 2, or 3, or 4, or 5, or 6. And so these 3 possibilities are the chances of winning. 15 different ways to wind up with 4 heads. They could be the first coin, the second coin, the third coin, the fifth coin, that kind of thing. 15 different ways to get 4 heads out of 6 coins. There's 6 different ways to get 5 heads. And the reason for that is one of the coins isn't a head, and any one of the 6 could be the tail. And there's only one way to get them all to be heads, and that's that all of them are heads. You add these up, and you get 22. So our probability of winning will be this. And notice that denominator. It is 2 to the 6th. And why it is 2 to the 6th is that these 2 add up to 2. These add up to 4. This one, this one, this one, and this one add up to 8. Powers of 2 are happening here. The 6th power of 2, 2, 4, 8, 16, 32. 6th power of 2 is 64. This is 22/64, which we're going to simplify to 11/32. Lovely thing about this problem is you start to realize, hey, this isn't a calculator problem at all. This is going to be pretty easy. And here's why. Our probability of winning is 11/32. Our expected value is $1.50. Now we're mixing our mediums here. We've got fractions and we've got decimals. So let's just pick one to work with. You know me, I'm fraction man. So here we go. 3/2 is equal to 11/32 times J. And this is the important thing. Whatever that jackpot is, you multiply it by this probability of winning to get an expected value that equals the cost of the game. That means the game is fair. All right. So, hey, look at this. A couple of 2's down here. We can cancel those things and get a 1 and a 16. That's fun. Multiply both sides by 16/11 to get rid of that. And you get that J is equal to 48/11. Now, this is kind of fun because as a mixed number, that's 4 and 4/11. Neat thing about the 11s. Everybody knows that 1/10 is 10%. But some people get kind of goofy and think, oh, then 1/5 is 5%. And 1/20 is 20%. No, 1/5 is 20%, and 1/20 is 5%, and 1/10 is 10%. But real close to 10%, 1/11 is 9%, and 1/9 is 11%. Well, this is 4/11, so that's 4 9%. And we're talking about money here, so this is actually equal to $4.36. So a jackpot of 436 would make this a fair game. Now, I don't think anybody's actually going to advertise that. Step up, pay 6 quarters for a chance to win $4 bills and a quarter and a dime and a penny because we love to get into our change drawer. What they would do is come up with a round amount of money on that. So if the jackpot of this game was something like $5, this carnival or this fair would lose money on this game because on average, people would win the $5 11/32 of the time. Let's go ahead and use this machine for that. 5 times 11/32. We actually have to do this? Well, we're going to do it anyway. 5 times 11 divided by 32. See, I could have done 55/32. Could have just done that. Anyway, that's about $1.72. So they'd be paying $5 to win $1.72 on average. That means the carnival will be losing 22 cents every single time they ran this game. Play 100 times, they've lost 22 bucks. They're trying to make money off of this. So they probably wouldn't choose a jackpot of $5. That'd be terrible. They had a jackpot of $4. Let's try that. That's going to be 44 divided by 32, right? Expected value of $1.37.5. So let's call that $1.38. People are paying $1.50 for an expected value of $1.38. The carnival is going to earn on average 12 cents every time this game is played. So that kind of jackpot would make this kind of profitable. Now, on that idea of profit, casinos actually make their money on these very, very tiny margins. And a fantastic example of this is the game of roulette. The roulette wheel is that big wheel, the ball goes around and around and around and lands on something. And most people that come up to the roulette wheel, either, you can bet on a particular number if you want to really take your chances, but most people are betting that it's going to land on either red or black. But there's some other squares on there. On either side of the wheel usually are green squares, sometimes a single zero, sometimes a double zero. And those greens are very, very, very rare, but they're not impossible, and they do happen. And when that happens, chances are that somebody hasn't come up and bet on green, so all the people that bet on red and all the people that bet on black lose, and the casino wins all that money. And it's that little gap right there that makes the probability of winning either one a little bit less than 50%, and that's how the casino is actually making its money. This game is something like that. If this is going for $4, expected value is almost the price of the game of that $1.50. Anyway, I hope that was a lot of fun. We're going to go ahead and stop now. No. Let's have full treatment. Erase the board, because that's what has to happen in class. All right, here we go. You guys having a good day? Anybody want to go to the bathroom? I thought about doing a lesson from the bathroom, but I thought better of it. Maybe by May I'll be, stir crazy enough to do that. Well, I hope you could hear some of it. I don't know how the camera is, like when I'm facing the wrong direction and all that. Goodbye.